Okay, welcome back, everybody. Um, just a quick note. We are on chapter 13 right now. Obviously, we got 2 chapters to go. 13, we'll finish it today, very short. 14's got about 35-ish slides or so. They may take 2 periods. And then the final chapter, which is 15, that's another short chapter also. So basically, we're going to have, I don't know, maybe 2, maybe 3 periods here that is basically, I call them just study periods, times that you can come in here, treat it as an office visit. I will be here during the times, and it's, voluntary. If you got questions, bring them in. If not, just get ready for the final. So anyway, just wanted to state that we're getting down to the wire pretty soon. We're going to have, let's see, next we'll have a break during Thanksgiving, and then come right back in a couple of weeks after that, be done with everything. So fairly short. So anyway, and the other thing is, don't forget today there is for chapter 10, there is a quiz that's required for the department. They're going to take those results and then compile them and use it for some type of evaluation. So don't forget about it. It's only got 1 shot. It is timed, and it does shut down at I believe 11:59 today. So, and I put it, it's worth 10 points, and I put it in the section for exams. So that kind of boost your percentage up a little bit if for your points that come from the exam aspect, from the exam, all the exams. All right, let's see what else. I think I got it all. All right, so let us continue then, and we're starting with chapter 13, unless there's some questions. If there are no questions, I will jump right in. All right, so this chapter deals with the term here called stoichiometry. Now, what I've been doing is every time we took an equation and we balance it, I asked you to look at the ratio, the coefficient, and then come up with a ratio between, let's say, reactants, A plus B. We had those coefficients tell us what the ratio is between A and B, and also between A, B, and then the product C, okay? Those coefficients allow us to get from point A to point B. Now, through all of these calculations, we can't go directly from grams of A to grams of B, or for that matter, to grams of anything, unless we go through the moles. So we have to learn how to convert grams into moles. And then furthermore, once we get moles, be able to convert moles to grams. Also, the coefficients allow us to go from moles of A to moles of B, for example, in the reaction of A and B. And that's what this whole chapter is all about. And we're gonna talk about that and do some sample calculations. The point being, with everything, with these calculations are going to be no different as far as set them up as we did when we did that chapter with respect to conversion factors, okay? We had a ratio that we set it up depending on what the question asked for, and we kept track of the units. We're going to continue that technique here, okay? So for example, let's take this reaction where we have nitrogen monoxide in the presence of oxygen to give you or to yield nitrogen dioxide. Now, keep in mind, what I did is I gave you the equation here in words, and you can end up with problems like that where you're given, like we've done before, given the problems in words, and then you take the words and convert them into a chemical reaction, then you balance them, and then 1 step further, then we do start doing chemical calculations. All right, so after we did the the balancing, we could say, and I've been saying the term, well, okay, in this reaction, it takes 2 molecules of NO to react with 1 molecule of oxygen to give me 2 molecules of nitrogen dioxide, okay? Now, if I, for whatever reason, I use 10 molecules of NO, well, given the ratio of nitrogen monoxide and oxygen, okay, given that ratio that we see here, that means that if I use 10 of nitrogen monoxide, I need to use at least minimum 5 molecules of oxygen. You see that ratio 10 to 5 is the same as 2 to 1, okay? And if I use 1,000 molecules of NO, well, I'm going to need half that amount of oxygen. Now, normally we don't talk about, individual molecules. We use the term moles. So what we say is it takes 2 moles of nitrogen monoxide to react with 1 mole of oxygen to yield 2 moles of nitrogen dioxide, okay? And keep in mind that 1 mole is equal to 6.02 times 10 to the 23rd, in this case, molecules. So it's quite a large number that we're working with, okay? Also, once we balanced it, I always would say, well, make note of the ratio, okay? We got the ratio of 2 NO to 1 oxygen. Okay, so that means that we can set up a ratio of 2 NO in the numerator and 1 O2 in the denominator, or we can invert it with O2 on top and NO on the bottom. Okay. There's also a relationship between the reactant NO, nitrogen monoxide, and nitrogen dioxide. It's a 2 to 2 or a 1 to 1. Okay. And also we can set up 2 ratios for that relationship. And then for oxygen and nitrogen dioxide, it's a 1 to 2 ratio. And I say 1 to 2 because I'm going from oxygen to nitrogen dioxide. If I went from nitrogen to oxygen, it's a 2 to 1, okay? So here from NO2 to oxygen is a 2 to 1. And from NO to NO2 is a 2 to 2, or essentially a 1 to 1 ratio. Okay, and these are the ratios that they're important for us to make sure that those coefficients are correct, because those are the ratios that are going to get us from moles of NO to moles of oxygen. Okay, given the ratio. So if I have 10 moles of NO, I'm going to need 5 moles of oxygen, because that ratio 10 over 5 is 2 to 1. Okay. All right, now this reaction, we have nitrogen in the presence of hydrogen reacts to give us ammonia. Okay, which means, another way to say this, that 1 mole of nitrogen requires 3 moles of hydrogen to yield 2 moles of ammonia, okay? And also note the ratio between reactants and products. All right, so coefficients gives us the mole ratios, what we call the stoichiometric relationship between reactants and products, okay? Yeah, there's a stoichiometric relationship all around us. If you think of a car and 4 tires, its stoichiometric relationship is 4 tires for 1 car, right? For a bicycle, that ratio is 2 to 1. For a tricycle, it's 3 to 1. Okay, and for a unicycle, it's a 1 to 1. That is that stoichiometric relationship between other items out here that we utilize on a daily basis. Okay, so let's take a look at this reaction here. We have 1 mole of iron 3 oxide reacting with 3 moles of carbon monoxide to yield 2 moles of iron and 3 moles of carbon dioxide. Okay, so that is a balanced chemical equation. You can double check. We have 2 irons on the left, 2 on the right. We have 3 carbons on the left, 3 on the right. We have a total of 6 oxygens on the left, and we have a total of 6 oxygens on the right. So, it's a balanced chemical equation. Then we take a look at the individual relationships, specifically between the reactants. And we have a ratio here, 1 mole of iron 3 oxide over 3 moles of carbon monoxide, or we can write it by inverting it, okay, where we got 3 carbon monoxide over the iron 3 oxide. And then, of course, we have the other ratios. I'm not just limited to here. So you have essentially this relationship. That's one pair. It's 2 ratios there. And then the iron 3 oxide to the iron, that's 2 more. So we got 2 here. Okay. And we got 2 here. I need 1 second, please. Okay, sorry, I'm back. Okay, so we have the first relationship between the reactants, and then the relationship between iron 3 oxide and iron. That's 2 ratios. And then iron 3 and carbon dioxide. That's 2 more ratios. So we got a total of 6 ratios there. Then carbon monoxide and iron, that's 1 relationship. That's 2 more. So it's 2, 4, 6, 8. Then carbon monoxide and carbon dioxide, that's 2 more ratios. 2, 4, 6, 8, 10 ratios. And then between the 2 products, okay? And so 10, we got 12 ratios here in this reaction that, we should become aware of, because depending on the problem, we could use any one of those 12, right? All right, so the question asked is this: how many moles of iron can be formed from a 10.2 moles of carbon dioxide? So for these type of reactions, the only concern we have is what the question asked about. So we're looking at iron, so I circle that, and carbon monoxide. So the only relationship that I'm concerned about is between the carbon monoxide and the iron. So we assume that the other material we can ignore. We're not concerned with those. We're only concerned between carbon monoxide and iron. We look at the question. It says, if I have 10.2 moles of carbon monoxide, how many moles of iron do I need? Okay, or can be formed, because it's a product. The assumption is that there's plenty of other iron 3 oxide involved to get this reaction to proceed. Okay, so we're only concerned about what the question asked about. Now, as we do any of these problems, what we do is we write down what we're given, right? We are given 10.02 moles of carbon monoxide. We know we're going to have a factor here, and then we write down what we're looking for, and what we're looking for is moles of iron. Okay, so that gives us a map. That gives us a map to where we need to go to. Okay. All right, so we need to find a relationship between carbon monoxide and iron. In effect, it's a 3-to-2 relationship based on the balanced chemical equation. So we put carbon monoxide in the denominator, right? Just like we done the other problems, what unit we need to get rid of, we put it in the denominator, because we're going to multiply the 10.2 times this factor. And then what we want on top of the numerator, unit-wise, is iron. Okay, so then we just plug in the coefficients that we get from the equation. And there we go. We're set up. So it's 10.02 times 2 divided by 3, and that will give us the number of moles of iron. Okay. Check your units. You can see their units of carbon monoxide cancel out, leaving us with units of iron. No different than what we did with respect to that conversion chapter. Okay. And it's keeping track of your units. Well, here we go. And so we require, what happens is when you start off with 10.0 moles of carbon monoxide, you will make 6.8 moles of iron. So you see how we went from A to B through the units of moles, plus through the coefficients of stoichiometry of A to B. Okay. All right. Excuse me. The second problem says how many moles of iron 3 oxide. So we're looking at this and we want to know how many moles, and I marked my equation so I can know what I'm working with, are needed to form 17 moles of carbon dioxide. So we need to make 17 moles of carbon dioxide. So our concern is the relationship between iron 3 oxide and carbon dioxide. What's happening with the others, we're not concerned about. Also, that relationship is a 1-to-3 ratio. 1 iron 3 oxide to 3 carbon dioxides. Okay. And this is a typical equation that we could do if, for example, if we were in the lab and we wanted to make X amount of product. In this case, it's carbon dioxide. Well, we need to calculate how much material we need to start off with reactant to make X amount. We don't arbitrarily go in the lab, just throw in a little of this, a little of that, like as if we're cooking. We actually have to calculate, okay, I'm going to try to make about 5 grams of this material so I can study it. Well, I need to know how much reactants I need to make at least 5 grams of this material. But keep in mind that in the real world, when you're out there in the lab working, you rarely make anything that's exactly that amount. That's a hypothetical amount that you actually calculate. And then you got an actual amount that you actually isolate. You basically divide that by the hypothetical amount, it gives you the percent yield. So anyway, let's go to the next problem. So what we're given is, we write down what we're given, 17 moles of carbon dioxide. Okay, we know we're going to have a conversion factor here. Furthermore, we know that factor is going to have CO2 in the denominator, right? And then what are we looking for? We're looking for moles of iron 3 oxide, okay? So that means that our iron 3 will be, unit-wise, will be in the numerator. All right, so that's a 1 that comes from the balanced chemical equation, and then the 3 that comes from the balanced chemical equation in the denominator. Check my units. Notice my CO2's canceled, leaving me with units of iron 3 oxide. So that has been properly set up. So 17 divided by 3 would be the answer. And that is 5.7 moles of iron 3 oxide are needed. So what this is telling you is, if I want to make 17 moles of carbon dioxide, I need to start with a minimum of 5.7 moles of iron 3 oxide. And then the other carbon monoxide is they probably run it in excess to ensure that you have enough to react with this. Okay, so this is run in excess, and then you start off with 5.7 moles of iron 3 oxide, and that theoretically would give you 17 moles of carbon dioxide. But like I stated, reactions rarely go to 100%, and you generally end up making a little bit less, and it varies from reaction to reaction, but you make less than 17. And so what you made divided by the 17 gives you a percentage yield. And obviously, the closer you can get to 100%, the better off, but that's very rare. Normally, depending on the reaction, you could be anywhere from 10% to 90% yield. Okay, so let's rehash here. What we've done so far is we have a chemical reaction. We looked at the stoichiometric relationship between the reactants and the products. Then we looked at the question. We set up the question by writing it out like we done any conversion factor. We write down what we're given, we write down what we're striving to get unit-wise, and then we have a conversion factor in the middle that then will get us from A to B, okay? A to B. Notice that we're working with moles, okay, at this point. That's fine right now. We're trying to get you to understand, you know, how the moles work to get from A to B. But keep in mind that once we have moles, we can go back to grams, because in the lab, in reality, we don't measure moles, we measure grams. We take what we measure in weight, and then we convert that to moles. Okay. So the next step logically will be to work with grams, convert that to moles, and then get to the moles that you're looking for via the stoichiometric relationship. And then once you get that, convert that to grams. All right, so, all right, let's take this reaction here. It says balance the equation. So, you know, if we put a 2 in front of the sulfur trioxide, that gives us 2 sulfurs and 6 oxygen. So if we put a 2 in front of sulfur dioxide, that balances everybody. Okay, we got a total of 2 sulfurs on both sides and a total of 6 oxygens on both sides. Okay. You might say, well, wait a minute, I only see 4. Okay, when I say 6 on both sides, that means take into account all the oxygens in different forms. We got 4 coming here and 2 coming here from oxygen. So that's a total of 6. All right, now, question number 1 says, how many moles of sulfur trioxide, so we're looking at this, will form if 0.165 moles of oxygen react? So our only concern is about the relationship between oxygen and sulfur trioxide. And we're starting off with 0.165 moles of oxygen. You want to know how many moles of sulfur trioxide will be made. Okay. So I'm not concerned about what's happening here, just what the question asks for. So we write down what we're given. Moles of oxygen, okay. And we're looking for moles of sulfur trioxide. So that goes in the numerator and O2 goes in the denominator. We go to the balanced chemical equation. It's a 2-to-1 ratio, okay? Our O2s cancel, leaving us with units of sulfur trioxide. So now it's just a matter of you plugging those numbers in the calculator, and you should end up with 0.330 moles of sulfur trioxide. Don't forget your sig figs, okay? Sig figs. These conversion factors, these coefficients are exact numbers, so they would not play a factor in the sig fig determination. Also, atomic weights do not play a factor in, to refresh your memory, do not play a factor in sig fig. So most of the time it's what you're given moles, which comes from a measurement. Okay, now second part. How many moles of sulfur dioxide, so we're looking at this, are needed to make 0.042 moles of sulfur trioxide? Okay, so our relationship is between the sulfur dioxide and the sulfur trioxide. And they're being asked, well, I need to make 0.042 moles of this. How many moles of sulfur dioxide do I need? Okay, all right. Write down what we're given. SO3. Okay. We are looking for moles of, excuse me, SO2. So SO3 in the denominator, SO2 in the numerator. SO3 is 2, SO2 is 2. It's a 2-to-1 ratio, 2 to 2, excuse me. Essentially 1 to 1, obviously the 2's cancel. Units here cancel, SO3 cancel, leaving me with SO2, sulfur dioxide. So if I need 0.042 moles of sulfur trioxide. Right? See my units cancel there, in there, leaving me with SO2 units. All right, so here's a flow chart, which will help you. And we're going to give you a flow chart here that's going to incorporate what we did earlier with the motor gas and put them all together, okay? But here's part of it. So in these type of calculations, generally you are given something in grams, okay? Just like we used to do the conversion factors, we're giving something in grams, and we are looking for something, some units. So this could be, A, and we're going to B. We need to figure out if we're given X grams of A, how many grams of B do we need? Okay, that could be the problem. All right, so we take the grams, and once we know the molar mass of A, whatever it may be, and it's the sum of all the atoms involved in this formula, and if we divide by the molar mass, that will give us the moles that we were given. That'll be the moles of A. Okay. Now, in the ratio, it's a ratio of B over A, for example, and X, whatever X may be, but that ratio comes from the balance chemical equation or reaction. Okay. And what that does is tells us how many moles that we're looking for. In this case, B. Okay. And so knowing the molar mass of B, over here we knew the molar mass, and generally we multiply by the molar mass. Over here we divide. We end up with the grams of B, whatever B is. Okay. And that's the guideline, but that's the how we're going through the problems. Grams of A divided by the molar mass gives us the moles that we're given. The mole ratio, the stoichiometric relationship of A to B, then gives us the moles of B. And then the molar mass of B gives us the grams of B. Okay, so in essence, what you can have in these calculations, you're going to have a minimum of 3 conversion factors. Maybe a molar mass to begin with, because you start off with grams. Then you're going to have the mole ratio in the center. And then you're going to have the molar mass of what you're looking for. Okay, so you're going to have 3 conversion factors. And if you set those up properly with the units set in the correct position, it just bam, bam, you're set up, check the units and just plug it in the calculator and you're good to go. Okay. All right, so let's take a look at this reaction where we have iron 2 oxide reacting with aluminum to give you iron and aluminum oxide. Now, who can tell me what type of reaction this is? What do you think? What kind of reaction is this? Okay, what we got? Combustion? Oh, not quite, not quite. Because remember, combustion, what do you need? You need oxygen, right? And plus a combustion reaction for Chem 130 will be just the combustion of hydrocarbons. Okay. Single replacement, that is correct. Single replacement. Remember the single replacement, you have an element, a metal. You got two metals. One of them is an element form, and the other metal is an ionic form. Okay. And what's happening here, the elemental form gets converted to the ionic form, okay, to form, in this case, aluminum oxide, and then the ionic metal gets converted back to the element. Okay. And is driven because aluminum, based on the activity series, aluminum is greater, more reactive than iron. And then the second question you ask is the most reactive metal in ionic form? Well, in this case, no. It's an elemental form, therefore reaction proceeds. Okay. So you could, typical type of questions are like what I just read. I can read it out, put this reaction in words. Iron 3 oxide in the presence of aluminum reacts to give you iron and aluminum oxide. Okay. Write the equation, name the type of reaction it is, and then do calculations. Okay. So those are typical type of reactions that could be asked. All right, so we have it here. And then we're gonna have two questions here. Okay, first one says calculate the mass of iron 3 oxide needed to react completely with 5.55 grams of aluminum. Okay, now thing to remember, isolate only the reactants and products that the question asks for. All right. And so here it's saying calculate the mass of iron 3 oxide. So I got the reaction, so I circle that. That's who I'm concerned about. And they want to know what is the mass, how many grams needed to react completely with 5.5 grams of aluminum. So my only concern is the stoichiometric relationship between iron 3 oxide and aluminum. That's all I'm concerned about. Furthermore, I'm told that I'm given 5.5 grams of aluminum, and I need to calculate how much iron 3 oxide I need if I start off with that amount of aluminum. Okay. Second part of the question, which here I will change the color, is this. It says calculate the mass of aluminum oxide. No, remember, you can't use blue. Let's do red. Of aluminum oxide. So my concern for the second question is this product. And I need to know, well, how many grams am I going to make when 10.25 grams of aluminum react? So in this case, I'm looking at aluminum again. And if I have 10.25 grams of aluminum, how many grams of aluminum oxide I'm going to make? Not concerned about the other species, because that's not what the question is asking me. Okay. And so this is the tricky part. I see a lot of the students say is that, okay, I got the balance equation, I got the reaction, I got it balanced. Then I'm asked a question and I'm like lost because I'm like, what are they talking about? And my suggestion is once you got that reaction, circle the entities that the question is asking about. Those are the guys that you have to worry about as far as the mole ratio between them and how many grams of whatever you're going from point A to point B. Okay. Everything else in the equation has nothing to do with the question. Okay. Don't let it confuse you. All right. So let's take the first one. All right. So from here, we're going from aluminum to iron 2 oxide. So we're only concerned about, okay, between the reactants. All right, so we start off with aluminum, 5.5 grams of aluminum, and we need to convert that aluminum to moles, okay? Because remember, we can't go grams to grams. We have to convert that to moles. So we take the atomic weight of aluminum. If it was the compound, it would be the molar mass, but in this case, it's just the element, so we just need atomic weight. Look it up on the periodic table, it's 26.92. So that gets us, if you look at the units, we are dividing by the atomic weight, grams cancel, leaving us with moles of aluminum, okay? The next coefficient, ratio, are the coefficients that relate the relationship between the aluminum and iron 2 oxide, and which is 3:2, okay? Since we're looking for a number of grams of aluminum, of iron 3 oxide, obviously that goes in the numerator. So if we were to stop the calculation right now at this point, then 5.55 grams of aluminum would tell you how many moles of iron 3 oxide, iron 2 oxide you would produce. But you want to go one more step, because we don't weigh things out with moles, we weigh things out in grams. So we need to convert those moles of iron 3 oxide to grams, and we use the molar mass of iron 2 oxide, okay? Note the units as we go along, we set this up, the units cancel out. We end up unit-wise with what we're looking for, right? We're looking for X grams of iron 2 oxide. So we have set the problem up correctly. The rest of it's up to you as far as plugging the numbers into the calculator and coming up with this number, 22.2 grams of iron 2 oxide. So what this is telling you is this. If I start off with 5.55 grams of aluminum, I need 2.2 grams of iron 2 oxide for this reaction to proceed, okay? That is what it's telling you, and that's what your calculation, and that's what you actually do in the lab, okay? You may weigh out an X amount of aluminum, you know, and that's your number for whatever reason. You weighed out 5.55 grams of aluminum. Now you got to figure out, how much iron oxide do I need? So you calculate. So once you calculate, now you know what is the minimum amount of iron 3 oxide you need for this reaction to proceed as written. Okay. The next one is, we're going from aluminum to aluminum oxide, right? Let's double check. Yeah, aluminum to aluminum oxide. All right, so we are starting from aluminum, which is 10.25 grams. And we need to figure out how many grams of aluminum oxide we're going to make. All right, so as in the first example, we need to convert those grams of aluminum to moles, okay? So we divide it by the atomic weight. It gets us into moles. Then the next factor gets us into moles of aluminum oxide, because that is what we're looking for. We're looking for how much aluminum oxide will be made if I start off with 10.25 grams of aluminum, okay? Meaning that everything else we're ignoring because we're not concerned about that. We have enough iron 3 oxide for this reaction. That's the assumption. You know, so we need to figure out how much aluminum oxide we're going to make. Check your units as you're going along. Okay, everything's canceling right now at this point. I'm in unit-wise moles of aluminum oxide, but I need to get to grams. So I need the molar mass. And so I add up the atomic weights for both aluminums and the 3 oxygens, and that should add up to 101.96 grams per mole. Okay, that is the molar mass. Okay, notice something. When we start in grams and we want moles, we divide by the molar mass. When we end up in moles and we want grams, we multiply by the molar mass. Okay. So with respect to units, we have units of grams of aluminum oxide, which is what the question asks for. Okay. So now you plug in the numbers. And that says that if you start off with 10.25 grams of aluminum, you will make 19.37 grams of aluminum oxide. At least that is the theoretical amount that you should make. Okay. All right. So this flow chart is your map to get from one type of calculation in moles to another in grams. Now I should say another type to get one compound in grams and move over to another compound in the reaction in grams or in volume, depends on what you're doing. Okay, like what we just did is we started off, for example, grams given, we had the molar mass that gives us the moles given. And based on the mole ratio of the chemical reaction, it tells us how many moles of what we're looking for, okay? And then based on its molar mass, it gives us how many grams. We convert that to grams of what we're looking for, okay? So that's the type of process. But keep in mind, if you're at STP, you can move on to figure out the volume using this relationship here, if we're dealing with gases, okay? And only at STP. So whenever you come up with a problem, print out this flow chart, and it will help you identify where you're at on this flow chart, and then that will assist you to get to point A to point B, okay? And just remember, the common factor to get from A to B is through moles. So I gotta get from there only through moles if I want to get from A to B. Okay, I gotta get through moles. Use moles as my common factor. All right, here's a reaction. So they're asking you, write and balance the reaction of HCl aqueous with solid cobalt, okay? They're also telling you that cobalt will be in the +2 oxidation state, simply because cobalt is not one of the 16 elements and metals that we know 100% their constant oxidation number, and it's a variable, so we have to tell you what it will be, okay? All right, so let's write down the reaction. And so we have cobalt as a solid, and then we have HCl, aqueous system. All right, can anybody tell me what type of reaction this reaction is? I give you a hint. Think activity series. Does that help you out? Oh, no, not quite. Not quite. It's a good thought. Not quite. In general, combination reactions, you end up with you start off with 2 elements, okay, to make a compound. Here you have an element and a compound to begin with. Okay, so this, what type of reaction do you use the activity series with? Remember the activity series in your periodic table? Right above the solubility rules. It's a single replacement reaction. And you're like, whoa, wait a minute, how's that? I don't have two metals here. I don't have a metal in ionic form. But if you look at the activity series, remember I circled it, that activity series is relative to hydrogen parentheses. And hydrogen, its ionic form is either be the proton H plus or H2. And so in here, instead of what you're doing is comparing the reactivity of cobalt versus hydrogen. Okay. And you will find that cobalt is more reactive than hydrogen. And if you recall also that, I pointed out from magnesium to lead, not an acid base. You're pretty close. It's a good thought though, acid base, because you see hydrochloric acid, but there's no hydroxide on the other side. That's cobalt. Okay. And so if you look at the activity series, right there, you see right here, H. Okay, the ionic form of H is H plus, or the molecular form, ionic form is H2. Okay, and so all the metals from magnesium to lead, and which I remember I said I call those M prime, just to designate them all from magnesium to lead. In the presence of HCl, they will create hydrogen gas plus the metal, in this case, chloride. Okay, and cobalt's right there. Cobalt's more reactive than hydrogen. So in this case, there is a reaction between cobalt and hydrogen, and we're going to replace the cobalt with the hydrogen. So we're going to make hydrogen go from ionic form to elemental form. That's hence you got the hydrogen gas. Plus the cobalt, they're telling you up here, has to be in the +2 state. Okay, they're telling you what it is. And we know that the chlorides are all -1. You need 2 of them. So cobalt would be CoCl2. Furthermore, it is aqueous, because if you look at the solubility of cobalt, other chlorides, you will find them to be soluble. Okay, so that is our reaction, and that is a single replacement reaction. All right, so now what we need is to balance it. Excuse me. And if you look on the left-hand side, we have 2 chlorides on the right, 1 on the left. What if we put a 2 there? Okay, so that balances the Cls, that balances the hydrogens, and the cobalts are good. So we have a balanced chemical reaction. Okay. Bam, there you go. Okay, remember, this is true for any of the metals from magnesium to lead. They will react with an acid to generate hydrogen gas and then the corresponding salt. In this case, the cobalt salt. Okay, everything's balanced. So now they're asking the question. All right, how many liters at STP will form if 5.0 grams of cobalt react, okay? And so they want to know how many liters of gas. Well, we look at the products, the only gas is hydrogen. And if we start off with cobalt, our only concern is the relationship between cobalt and hydrogen gas. And if we have 5.0 grams of cobalt, how many liters of hydrogen gas we are going to react, okay? That's what they're asking. So we write down what we get, what we're needed, what we're given, right? We also write down what we're looking for, liters of hydrogen gas. Okay, so they keep track of, help us keep on the roadmap. All right, so we had the first step is to convert the grams to moles. So we look up the atomic weight for cobalt, which is 58.93. Okay, that gives us moles of cobalt. Okay, now what we need is what to relate the moles of cobalt to the moles of hydrogen. And that comes from the balanced chemical equation, okay, because it's a 1-to-1 ratio. So notice now, unit-wise, all the cobalt, grams of cobalt cancel, moles of cobalt cancel, leaving us with moles of hydrogen, okay? So at this point, unit-wise, we are at moles of hydrogen. And the question is, how many liters of hydrogen would that be if you start off with 5 grams of cobalt? Since we are at STP, always remember this relationship. The 22.4 liters per mole, okay? So at this point, with respect to units, we are at liters of hydrogen gas, okay? And so that corresponds to 1.90 liters of hydrogen gas, okay? So what that tells you is this: if I start off with 5 grams of cobalt, I will make 1.9 liters of hydrogen gas. Okay. In essence, if we go back to the flow chart, we went from here to here. Okay. And if you had the flow chart in front of you, that's how we went. That would help you out. Okay. Now here's asking you if 2.374 liters of hydrogen gas is formed, if we started off with, if we made 2.374 liters of hydrogen gas, how many grams of hydrogen chloride, HCl, were reacted? So what we're concerned about is simply the relationship between HCl and the hydrogen gas, okay? So we start off with what we're given, 2.374 liters of hydrogen gas. We're at STP. That allows us to use the 22.4 liters per mole relationship. This then gets us into moles of hydrogen. Okay. The next factor is from the balanced chemical reaction. The stoichiometric relationship between HCl and hydrogen gas is a 2-to-1. Okay. Once we're there, this puts us into moles of hydrochloric acid. So the next one would be the atomic molar mass of HCl, which is 36.46 grams per mole. And that will put us into grams of HCl. So notice our units here, how they all cancel, leaving us with the grams of HCl, which is what the question asks for, okay? So now you just plug those numbers in to your calculator, and you should come up with 7.73 grams of HCl. Keep in mind with respect to HCl, excuse me, with respect to sig figs. The only factors that could play a factor is obviously this conversion factor, which is a measurement. So the 22.4 liters could be a factor in sig figs. And it is in this case because we start off with 4 sig figs, okay? The 2 and the 1 are exact numbers, and the atomic weights, molar masses, are not used to determine that because remember, they are an average, weighted average of whole numbers. So they have an infinite number of sig figs, so we don't use them. So in this case, the 22.4, which has 3 sig figs, defines the number of sig figs you have as your answer. All right, here's another problem here. And we won't have too many more left. It's HCl plus hydrogen gas produces chlorine gas and water vapor, okay? And so we basically just write what we read here. HCl gas plus oxygen gas produces chlorine, it's diatomic, which is a gas, okay, plus H2O is a vapor, also in gas phase. Okay, so if I put a 2 in front of HCl, that does balance out my Cl's on both sides, my hydrogens, but my oxygens are not balanced out. So if I put a 2 in front of water, that does balance my oxygens, but then that kicks up my hydrogens, so I got to kick my hydrogens up to 4, okay, which means my chlorides now are at 4. So if I put a 2 in front of Cl2, now I got balanced chemical reaction. 4 hydrochloric acids per 1 oxygen to yield 2 chlorines and 2 waters. Okay. The question is, how many liters of chlorine? So how many liters of chlorine can be formed if 3 liters of oxygen react completely at STP? So our concern is between the O2 and the chlorine gas, and we are at STP. Okay, so we put down 3.00 liters of O2. Okay. We're going to convert the O2 into moles of O2 using that relationship because we are at STP. Then from a stoichiometric relationship, it's a 2-to-1 ratio, which then will put us into moles of chlorine. And once we're in moles of chlorine, we need to get into volume of chlorine. And again, we use the relationship of 22.4 liters per mole, okay? So that means that we end up with 6.00 liters of chlorine. Now, if you observe something pretty interesting here, that if all the reactants are in the gas phase, you notice, and that you are at STP, that's important, that you're on STP, everybody's in the gas phase. Notice that we use the 22.4 liters on both sides of our coefficients. Well, they cancel each other out. So we simply just use the stoichiometric relationship between the gases, okay, without having to put in the 22.4 liters. Now, until you're comfortable with this, yes, go ahead and put them in on both sides until you're comfortable with the fact and you observe that then at that point, you can simply use the stoichiometric relationship between the two chemicals in question here, without having to put 22.4 liters on each end, because they cancel each other out. But do put them in there until you're comfortable and you recognize it. Okay. All right. But only if it's at STP. So I would try these at home. In fact, I'm gonna run through them about 15 minutes. But carbon reacts with oxygen gas to form carbon monoxide. Okay, so let's write that reaction. carbon plus oxygen gas, diatomic, carbon is solid, reacts to form carbon monoxide, okay, which is also gas. All right, so to balance things out, we have put a 2 in front of carbon monoxide to balance the oxygen, so it kicks up my carbons. So I just need to put a 2 in front of carbon, and we are balanced, okay? 2 carbons on the left, 2 on the right, 2 oxygens on the left, 2 on the right, we're balanced. Now, question is, how many liters of carbon monoxide? So how many liters of carbon monoxide at STP? We're at STP, so being at STP, we can use this relationship per mole. Can be made from 15 grams of carbon, right? So that's what we need to do. You got to go from 15 grams of carbon to liters of carbon monoxide. All right, so if we start off with 15 grams of carbon, we're going to need, it's atomic weight, because we need to convert those 15 grams of carbon to moles of carbon. Okay. Then we see that there's a relationship between carbon monoxide and carbon. It's 2 to 2, 2 CO, 2 carbon monoxide to 2 carbon. So that would give us the moles of carbon monoxide. And if we do the final one at 22.4 liters per 1 mole, that will put us into liters of carbon monoxide. Okay, you see how my units cancel here? All right. So 15 grams, you convert to moles of carbon. Then the stoichiometric relationship between carbon monoxide and carbon. And then finally, since we are at STP, convert that using the 22.4 liters per mole to get the moles, to get the liters of carbon monoxide, okay? And then try that with the 20 liters, and you should get, I'll give you the answer now, it's 28.8 liters of carbon monoxide if you start off with 15 grams of carbon. And if you start off with 20 liters of oxygen, you should make 40 liters of carbon monoxide, okay? So try these at home. If you have any challenges with them, bring them on Thursday. And like I stated earlier, we're going to be spending more time. We're going to be finishing up soon, so we're going to be spending more time here as like study sessions. So I'll be doing less office hours, and that time will be spent here. So thing to remember about this chapter: use the flow chart in the calculations. The flow chart will get you from point A to point B. Okay, and the takeaway is this: convert things to moles to get you from A to B. Okay, you got to get into moles. That, ladies and gentlemen, brings you to the end of chapter 13, excuse me. We would just need chapter 14. And for those of you who came in a little bit late, 14, probably about 35 slides, maybe 2 sessions. And then chapter 15 is 10, 11 slides, very short. So in essence, I would say in the next 4 Zoom sessions, we'll probably be done with all the lectures. And then what is remaining, we would use as time for you. So start coming up with, you got questions about any of the chapters, start making a grocery list about those questions, and then bring them into class and we'll go over them. Okay. All right. Let me stop this, and